The Eiffel Tower, a symbol of Paris, the pride of France, and supposedly a flawless marvel of engineering. That's exactly how it's presented to us. But what if this story contains far too many things that simply shouldn't add up? Overly rushed timelines, suspiciously precise assembly, a far too convenient official narrative, and too many strange traces that have either vanished or seem deliberately left out of the frame. Let us know where you're watching from and subscribe to the channel. Thank you. 2.5 million rivets in 26 months. On paper, it sounds like a record. In reality, like an almost impossible task, especially when you consider it all took place at tremendous heights, in the cold and wind, with red-hot metal in hand, and virtually no room for error. But that's not even the strangest part. Why have documents on key technical details seemingly vanished? Why do photos from the construction site show so much, yet seem to avoid the most crucial elements? Why does the tower's metal behave as if it defies the ordinary logic of time? And most importantly, why do old maps of Paris show something strikingly similar to this tower long before its official construction began? Today, we're unpacking a story that appears complete on the surface. But the deeper you go, the stronger the feeling becomes that what we're looking at isn't just a 19th century construction project, but a carefully assembled version of events, one riddled with cracks. 2.5 million rivets in 26 months. There's something unsettling in that number alone. To the ear, it sounds like a neat detail from a museum plaque, but pick up a calculator and the polished version starts to crumble. Divide the total by the construction period. That's roughly 3,200 rivets per day, every single day, without long pauses, without delays, without slowing down. Now let's go further. If the workday lasted about 10 hours, that's around 320 rivets per hour, which means 5 to 6 rivets per minute. Not occasionally, not at peak times, not on a good day, but constantly, day after day, for nearly 2 years straight. And here's where it gets interesting, because a rivet isn't a button you simply push into a hole. It's a piece of red-hot metal that first has to be heated to nearly 900 degrees Celsius, then quickly carried to the work site, inserted, clamped, forged, shaped into a head, all before the metal cools and becomes a useless lump. On paper, the math looks dry. In reality, behind every point in the report lies a separate operation, a separate movement, separate seconds that can't be wasted. Now imagine this frantic pace wasn't required in a warm workshop, but at a dizzying height, where metal cools faster than you can blink, where every step is taken over a void, where a mistake isn't just a delay, it breaks the entire chain. Then the main question isn't whether 2.5 million is a lot or a little. The real question is, how could such a tempo even be maintained in an environment that worked against the workers themselves? Now put the calculator aside and picture where these numbers had to turn into metal. The Champ de Mars, winter, the structure already towering over the city, and the higher the frame rose, the less it resembled an ordinary construction site. It was no longer a workplace in the usual sense, but a delicate grid of beams suspended over emptiness. Underfoot, a narrow strip of iron. On either side, nothing but air. One wrong step, one sudden gust, one awkward shift of balance, and even a simple task becomes a risk. At such heights, everything changes. Down below, the wind is just cold. Up here, it pushes at your shoulder, tugs at your clothes, throws you off balance. On the ground, red-hot metal still gives you a margin of time. Up here, that margin shrinks. What looks like heavy but manageable work in a workshop becomes a race against seconds. You have to keep your balance, watch your tools, maintain the pace. hear your partners over the howling wind, all while working as if conditions were normal. But normal conditions were long gone. And this is crucial, because the official description of the construction is often presented as a perfectly tuned machine. People in place, processes streamlined, pace maintained, results delivered exactly on schedule. Only the site itself contradicts that image. There was too much instability, too many factors that couldn't be switched off. Height, cold, wind, limited space. These weren't just background elements. They were active participants in the build. And if this was the working environment, then the next thing to examine is a single rivet. Not in a report, but in real motion, from the forge to the strike of the hammer. A single rivet in this story weighs very little, about 100 grams. But in essence, it's not a small part. It's an entire operation that had to be carried out quickly, precisely, and without fail. First, it's heated in a portable forge. The metal must reach nearly 900 degrees, becoming soft, malleable, ready to be shaped. At this point, the rivet glows a deep red, almost cherry. Then the countdown begins, where every second matters. A worker pulls out the glowing rod with tongs and passes it on. A partner must immediately place it into a pre-aligned hole, waiting for exact placement. On the other side, someone holds the support so the head doesn't shift or deform. Another worker, sometimes two, begins quickly forging the protruding end with heavy blows, shaping it into a second fixing head. While the metal is hot, it obeys. Once the temperature drops, it's over. Too late, and the part has to be punched out, drilled, and started anew. That's why the dry figure of 5 to 6 rivets per minute no longer sounds like a production record, but like an almost unattainable pace. Because it's not about one movement, it's about an entire chain. Heat, carry, catch, insert, hold, forge. And without stopping, without fumbling, without mistakes. Any hiccup breaks the rhythm of the whole team. Any delay eats up seconds that were already in short supply. Add height, wind, and awkward positioning to that, and even one successfully placed rivet looks like the result of a perfectly coordinated team. And that raises the next question. If every such operation required heat, pace, and precise coordination, where did the site get the fuel, the forges, and the sheer ability to maintain this rhythm hour after hour? And here, the construction project hits a limit not of manpower, but of supply. Because a red-hot rivet doesn't appear by itself. It needs heat, constant, stable, predictable heat. Company documents mention a peak coal consumption of about 3 tons per day. At first glance, that's a substantial figure. But do the math again, and it stops looking like a bottomless reserve. One portable forge, capable of maintaining the necessary temperature for riveting, consumes roughly 20 to 25 kilograms of fuel per shift, sometimes more. Theoretically, 3 tons could supply a large number of forges, but only on paper. On the actual site, coal wasn't used just for rivets. It was needed to heat the workers' huts, to shape metal, for auxiliary tasks, to feed people, to sustain the entire living rhythm of the construction. After all that, what remained for the riveting itself wasn't an unlimited reserve, but a very firm ceiling. And then an inconvenient picture emerges. There are many crews. Each needs its own heat source. Each must receive red-hot metal without delay. But the more crews, the faster the fuel dwindles. and the fewer forges, the harder it is to maintain the pace suggested by the official numbers. It's precisely here that a strange explanation appears, the so-called chain method. Allegedly, rivets were hoisted up in special insulated containers so they wouldn't cool on the way. The idea sounds neat, almost too neat, because without such a system, the logistics start to fall apart. But then there's a void. No containers, no blueprints, no patents. Museums have preserved tongs, hammers, braziers, small tools, even everyday items from the site. But the key link, without which the whole chain loses its meaning, seems never to have existed. And if the heat supply is so murky, then it's time to look deeper. Not at the fuel, but at the structure itself, where a single error in one joint could derail the entire plan. Now we must look not at the whole tower, but at a single point where all the beauty ends and engineering rigidity begins. Any large framework is held together not by its overall silhouette, but by its joints, places where several elements converge at once. It's there that you see how plausible the whole story is. The Eiffel Tower has thousands of such points, and each is not just an intersection of iron strips, but a complex spatial connection where beams meet at different angles, bear different loads, and must function as a single body. Take a typical joint at mid-height. 4 elements might converge there: diagonals, a horizontal brace, a main load-bearing strut. Each has a series of rivet holes. In total, dozens of fastening points accumulate at one such joint. And here's the key. For all this to come together without distortion, each part must be manufactured with almost no margin for error. Not just in length, but in angle, edge geometry, the position of every hole. If even one beam is off by just a little, the misalignment will start to accumulate, and at the meeting point, you won't get a clean assembly. You'll get a struggle with the metal. It's here that the dry term tolerance starts to sound almost threatening. When dealing with beams several meters long, a tiny deviation is enough for the holes to stop lining up. And without aligned holes, riveting simply can't begin. You can't force a rivet into metal like a nail into wood. It must go where everything has been prepared and aligned with high precision in advance. This leads to a very uncomfortable conclusion. A tower of this scale required not brute force, but almost jewel-like coordination of thousands of parts. And after that, the next, even tougher question arises. What tools in the late 19th century could possibly achieve such a fit without modern machinery and digital geometry? And here the tower faces its most uncomfortable question. Not how much iron was needed, nor how many men stood on the beams, but what exactly in the 1880s could ensure such precision? Without CNC machines? Without computer models? Without laser surveying? Without the familiar technology that today holds complex structures within a millimeter. Engineers had paper blueprints, manual marking, drilling machines with far more modest capabilities, plumb bobs, tape measures, squares, theodolites. For their era, it was a serious toolkit. But the question is the scale of the task. When assembling a single frame or a small bridge joint, manual precision still seems realistic. But here, we're talking about thousands of unique parts, each of which must not just fit by size, but occupy its exact place in a vast spatial scheme. Even if the factory worked flawlessly, even if the craftsmen were first-rate, any minor error in a hole, a length, an edge angle would start to propagate through the structure. At the bottom, it might go unnoticed, At the top, it would become a problem that couldn't be hidden by a pretty report. This is why engineering logic suggests a simple solution: on-site adjustment. First, holes are made with extra clearance. Then, when the parts are brought together and fixed, they are carefully reamed to the final size. It's slow, tedious, very labor-intensive, but plausible. This removes the microscopic misalignment almost impossible to avoid in a large assembly. But in the official history, this heavy intermediate work is almost absent. Everything is presented as if sections arrived on-site, ready-made, and slotted together like perfectly fitted toy blocks. And if the most important technical bridge disappears from the story here, then we must check not the tools, but the very physics of the metal, which at such heights lives by its own laws. But even if we assume for a moment that the parts somehow did converge with high precision, there's another force that intervenes in the construction unasked. That's temperature. Iron is not the same throughout the day. It lives, breathes, expands in the sun, and contracts in the cold. For a small part, it's almost unnoticeable. For a beam 10 meters long, it's millimeters. And millimeters in such a structure decide everything. Imagine an ordinary morning. The air is cool, the metal not yet heated. An element occupies one position. A few hours pass, the sun rises higher, the dark surface quickly absorbs heat, and the same beam becomes slightly longer. You can't see it, but for holes that must align with almost no play, it's enough to cause problems. What fit in place in the morning might, by noon, be pulling on a neighboring joint, binding, causing distortion, hindering the fit of the next part. The tower becomes not just a set of iron pieces, but a huge organism constantly changing its geometry. Today, such things are planned in advance. Engineers make adjustments, model thermal behavior, and understand when and under what conditions to install a specific component. By the late 19th century, theoretical knowledge of metal expansion already existed. But knowing the formula is one thing. Manually calculating the temperature's effect on thousands of unique parts in a giant vertical structure is another. This is no longer just a complex construction project. It's a task where physics itself begins to work against a beautiful legend. And here, the official account becomes especially suspicious. It speaks in detail about triumph, deadlines, height, and the courage of the engineers. But it hardly pauses to explain how exactly they tamed the metal, which changed size throughout the day, right during assembly. Which means it's time to step back for a moment and look at how this flawless story appears when told the way it's usually presented in textbooks and museums. If you view the tower's history through the lens of the official version, everything looks almost perfect. There's a talented engineer with a famous name, a bold project for the World's Fair, precise calculations, discipline, determination, and a brilliant result. Eiffel's company gets the contract. Foundations are laid near the Champ de Mars. The 4 pillars rise higher and higher. Then platforms emerge one after another, and above them, the famous silhouette that would soon become a symbol of Paris. Deadlines are met. The budget doesn't balloon. The team works like clockwork. The summit is conquered. The flag is raised. The world gets a new marvel of engineering. That's why this story has taken root so well. It's convenient. Everything fits. Progress, genius, the industrial age, the triumph of engineering. This material easily makes for museum displays, school paragraphs, and inspiring lectures about how a bold idea turns into metal. The problem lies elsewhere. The prettier the official picture looks, the more glaring the details that don't fit become. The pace is too fast. The assembly is too smooth. The metal is too obedient. The accounting is too clean. There are too few traces of the heavy, dirty, exhausting work without which such a structure simply doesn't come into being. What we see is not just a successful project, but an almost perfect project. And perfect projects are rare in reality, especially where there are thousands of parts, a harsh environment, manual labor, and a constant struggle with weight, wind, and time. This is where things get interesting, because the legend holds up only as long as we look at it from a distance. But as soon as you place the Eiffel Tower next to other major structures of that era and ask a simple question, why did everything here turn out so much faster, more precise, and cleaner than the others? The certainty begins to crack, and the next step becomes obvious. If the tower truly was such an incredible leap forward, it should be visible in comparison with other major construction projects of its time. So now, the tower needs to be placed not alongside its legend, but alongside other large construction projects that also involved metal, calculations, ambitions, and grand promises. And the comparison becomes uncomfortable. Almost simultaneously with the Parisian Tower, Tower Bridge was being built in London. A large, complex, prestigious project with a powerful steel frame and serious engineering demands. But it took 8 years to erect. Yes, the design was different. Yes, the tasks varied. But the principle remains. The more complex the structure, the more time it requires. Here, we see the opposite. A tower that reaches into the sky somehow appears faster than a lower, more accessible assembly system. There's another example. The frame of the Statue of Liberty was designed by the same engineering school, the same people, the same circle of specialists. The height is incomparably smaller. The mass is too. And still, that work took years. Not months, not a miraculous sprint, but a normal, heavy, plausible time frame. This is especially important, because when the same team moves at the era's usual pace on one project, but suddenly achieves almost fantastical speed on another, you can't help but look not for inspiration, but for a hidden explanation. Even if we look at later times, the contrast doesn't disappear. Modern towers are built with powerful cranes, precise surveying, computer calculations, welding instead of slow riveting, and the timelines are still long. Not because engineers have become weaker, but because large vertical structures themselves don't tolerate haste. They demand time. And the more we compare, the less the story of the Eiffel Tower resembles just a successful project. It begins to look like an exception that stands out too sharply from the rest. And when the timelines stop convincing, the gaze naturally shifts to the next level, the material from which this structure was assembled. The material in this story is no less important than the timelines. The tower was assembled not from the structural steel we're used to, but from puddled iron. For the late 19th century, this was a logical choice. Such metal is softer, more ductile, better handles stress in riveted joints, and doesn't behave as capriciously as early steel. But this is precisely where a new layer of questions arises. Because puddled iron isn't the product of a button and automation, but heavy, old-style metallurgy, where everything depends on furnaces, manual labor, time, and enormous effort. To obtain thousands of tons of such material, simply melting pig iron isn't enough. It needs to be refined for a long time, purified, forged, turned into blanks, then into profiles, then into parts. It's an entire industrial chain, slow and voracious. And when it comes to over 7,000 tons of iron for a single project, the question becomes acute. How quickly could suppliers deliver such a volume exactly when needed, exactly of the required quality, and exactly for such a precise task? On paper, the answer is simple. France's large-scale industry managed it. But the deeper you look into the process, the less straightforward that answer seems. There's a second, even stranger point. Over decades of operation, the tower's metal has performed too reliably. Wind, heat, cold, daily fluctuations, the constant work of the entire structure. All of this should have gradually accumulated fatigue in the joints and elements. That's how any large frame behaves. It's inspected, reinforced, partially renewed, because eternal structures don't exist. But here we have an object that seems to have proven stronger, not only than the expectations of its own century, but also many later systems. So a curious gap emerges. On one hand, we're told about a material of old technology, heavy to produce and limited by the era's capabilities. On the other, this material behaves as if its safety margin was calculated not for a temporary exhibition object, but for a very long life. And after that, it's impossible not to move to the next layer. If the metal behaves unusually, then it's worth looking even more carefully at the traces of the construction itself, the photographs, documents, and people who should have left far more noise in history. The longer you look at this story, the stranger the behavior becomes, not just of the numbers and the metal, but of the construction evidence itself. An object of this scale should have left a vivid trail, dozens of striking reports, workers' memories, detailed descriptions of the most challenging phases, live scenes of section lifts, debates, accidents, everyday details. Instead, what remains feels like a carefully arranged display. There are many photographs, but few perspectives. Almost everywhere we see the tower from below, a beautiful silhouette, dramatic figures on beams, poses that make a strong impression. A man with a hammer, a man with pliers, a man sitting above the void. The shots are powerful, recognizable, almost symbolic. But where is the work itself at the decisive moment? Where are the photos of heavy sections being lifted? Where is the complex bustle around the joints? Where are the scenes of synchronized crane work, if that's what supported the entire logistics of the upper tiers? Almost none of this exists. We see the result and the preparation, but not the nerve of the process itself. And that's especially strange for a project that, from the very beginning, was meant to be a showcase of the industrial age and a source of pride for its organizers. The people raise just as many questions. They appear in payment records. They flicker through newspapers as a faceless mass. But personal voices are almost never heard. There are no memoirs from ordinary assemblers, no well-known diaries, no later accounts from those who could say, "Yes, I stood up there and saw how it was really done." For a construction project of such symbolic scale, the silence feels too thick. And then another detail surfaces. Later, in the story of the Panama Project, discussions emerge alongside Eiffel's name about strange personnel policies, high payments, and weak transparency. And that's when an uncomfortable thought takes shape. What if the silence around the tower isn't a random gap in the archive, but part of the picture? And if direct evidence behaves so uncertainly, we're left to look at indirect traces, and they lead in a completely different direction, to old maps of Paris, where a mysterious vertical structure appears before its official birth date. And here, the whole story reaches its most dangerous threshold. Because after the strange numbers, the overly polished legend, the silent archives, and the unusual behavior of the metal, one question remains that isn't so easy to dismiss. What if, in 1887, they didn't start building the tower from scratch on the Champ de Mars, but instead had access to some already existing foundation? Not necessarily in the form we know today, not necessarily with arches, platforms, and the familiar silhouette, but possibly with a ready-made frame that was later modified, reinforced, clad, and adapted for a new era, and for a new official narrative. Then the unusually fast timeline starts to look less like a miracle and more like a logical task. Then the frantic arithmetic of rivets no longer seems necessary to explain the entire structure. Then the precision of assembly no longer seems so impossible if a large load-bearing part was already in place. Then the old maps with a mysterious vertical structure on the Champ de Mars stop being a historical curiosity. They become a clue that the official version would rather turn away from. And that's why, in this story, the Eiffel Tower becomes not just an engineering monument, but a door to a much broader narrative. World's fairs, vanished pavilions, grand structures that seem to appear too quickly and then disappear just as fast, as if someone was in a hurry, not only to show the world a picture, but to erase unnecessary traces. Perhaps what we're seeing is truly the triumph of the industrial age, or perhaps it's just a very convincingly packaged version of events. It's up to you to decide how to look at it. If this story made you think, give it a like, subscribe to the channel, and hit the bell so you don't miss the next investigation. It's only going to get more interesting from here. See you next time.